Hello, everybody. Thank you so much for joining us today. So it's a special webinar today because it's the last one of the year for Event Store with the lovely Stephen. And today, this is actually being turned into a two-part webinar series.
Yeah, hi everybody. My name is Stephen. I'm a developer advocate for Event Store. Just want to talk a little bit about event sourcing and its design principles, and I'm going to use a little bit of example from unique constraints a little later on. First of all, I just want to make a quick apology. When I was designing this webinar. I was going to first of all talk about mostly talk about unique constraints. But slowly I realized that to talk about that, there needs to be a lot more kind of foundational principles and concepts that I think a lot of learners need to know around event sourcing. And so I decided to split this up into two series where this first part that I'm going to be talking about would be more about the foundational concepts that we will going to be applying into a second part where I'll be talking more about unique constraints and how those principles will apply and give the kinds of trade-offs that we need to consider when we do designs like that. So apologies for those who are here today expecting that it's going to be fully about unique constraints. Just a note that that is going to be in the part two that we think hopefully will be coming up soon after the holidays. So without further ado, let's begin with this. So data consistency can be a very important part of a business application, especially when data is complex, right? And these data are usually frequently updated, they're widely distributed, and has many different business constraints. When we're talking about data consistency, we're generally referring to two things. So the data set that satisfies a list of business rules or constraints. And also, the data set is also synchronized correctly across all the systems. So most developers would agree that data consistency is something that is worth striving for. But despite its importance, many modern applications are not really great at enforcing data consistency, and this often leads to a lot of data loss, duplication, and other kinds of inconsistency that often requires a lot of data cleanup and an effort downstream. So from my own personal observation, right, the cause of this, I think, is largely more on education, and most developers are not aware of application patterns and concepts that are required for building consistent applications. And through our learning as developers, right, a lot of us may think that the database transactions alone is enough to keep your data consistent, but this has not really been the case anymore since the distributed and internet age, where your data is expected to stay consistent, not just within your app, but across hundreds and thousands of servers as well. So in this two-part webinar series, we're going to take a look at how event sourcing and some of the patterns and concepts and principles around it can help you build more solid applications that can survive the test of time. In this first part, we're going to talk about some of the essential patterns that you need to know. We will talk about aggregates. We're going to talk about transactional versus eventual consistency boundaries, and what it takes to draw them. And in the second part of the webinar, we're going to talk about how event sourcing aligns with these concepts, when to use it and when not to use event sourcing. And then we're going to apply everything that we learned to a unique constraint example where we can go through the different trade-offs and scenarios. So to begin this webinar, we're going to dive real deep and talk about, first of all, how we need to design our object model in our code base in order to enforce data consistency. So to begin, we're going to go back to school and the basics of objects and object-oriented programming. So An object in object-oriented programming is an instance of a class that has a set of data and functions. Right? So data is a collection of attributes that are usually updated by the object's functions. And objects often references other objects and can call their functions as well. And this means that objects can update data of other objects. And so, for example, maybe a purchase order, right, is an object that references multiple line items. Okay. And this network of references form an object graph or trees that represent a slice of the business in an application. An application can typically have anywhere from like a few hundreds to maybe even like a few million or even more object graphs. So, for example, maybe a small company may have like a few hundred purchase orders at the time, but a larger enterprise might have like millions and millions of orders, so which forms millions of object graphs. So, it is common to have business rules over objects that dictates how the object's data have to satisfy some constraint. So, for example, so maybe in a supermarket inventory system, the product object, its price might need to be greater than 0. In a hotel booking system, right, the booking object must have a booking date. And then for a credit card object, the credit card number itself must match the format of its card type. So say maybe MasterCard must have 16 digits. So these business rules are in place to ensure consistency throughout the system so that the business and programmers can make useful assumptions that can help understand the system better. It can also help programmers to better understand the nature and the behavior of the objects themselves. When a rule is defined only on a single object, like what we have here, the rule can be easily enforced by just adding validation logic to functions that manipulate the data in question. And when the function call, when a function call can breaks the rule, the validation logic intercepts and fails the call. So rules are quite simple if it only involves one single object. On the other hand, let's see how things are like when you have rules that are a little more complicated. So when rules span across multiple objects, the rules become harder to enforce. So say if we have two simple objects here that share a simple rule where the color in both objects must match at the same time. So say here, if the color properties in both objects are the same, the rule is satisfied. If it's not, then it fails. So for this rule to be enforced, there are generally two approaches in how we design the objects. So on one hand, say the first approach would be where you only one object, like a more like a kind of like a leader or a master object, can update the color on both objects. Okay. The second approach would be both objects, they both have references to each other and can update the color on each one of them. So the first approach will only have one reference, where the second approach will need two references so that either one can update each other. So the first approach will rely on sort of like this gatekeeper to manage updates and enforcing the rules, and has less references, as you can see on the top. The second approach, however, will lead to a lot of like cross references with other objects and probably a lot of duplicated code as well too. So, and it's not very common like out in the field to see objects with multiple references to with each other. So for the rest of this talk, we're going to be talking about how to enforce rules with this kind of single gatekeeper approach. So there are a few characteristics of this gatekeeper pattern, and it's at number one, there is generally a rule that spans across a set of objects, like what we have here. And secondly, there is one single object that acts as a gatekeeper to enforce that rule. And while this single gatekeeper is more or less like a simpler approach, as your object graphs gets bigger and bigger, it still needs to be implemented very carefully in order to keep things consistent. So, for example, if we allow other objects, external objects, to bypass the gatekeeper and talk to one of its kind of child objects, then it can possibly change the child object into something that can break the rule. So in order to protect the child objects, it cannot be exposed to objects that are outside of the object set itself. And this means that no objects outside can really reference them. And if any object wants to change any of the objects inside the set, it must go through the gatekeeper. So in object-oriented programming, this can be implemented as a composition object where the child objects are encapsulated or hidden by private access modifiers. And implementing the gatekeeper as a composite keeps the rules in one place so that it can be enforced on its objects. So here we see that another characteristic of the gatekeeper is that the gatekeeper's objects cannot be referenced by objects that are outside. I'm going to talk about like a final characteristics of this gatekeeper like pattern, and it has to do with saving things to the database. So most data in business applications have to be saved to disk or database. And if the gatekeeper's job is to keep its objects consistent, it has to ensure that the data stays consistent even while it's being saved to the database. This is pretty simple when there is only one single user that can update the object. So see here, for example. However, when there are multiple users in the system, this can really cause some issues. So say here we have two users who are concurrently trying to save the same object at the same time, but with a different value. However, since the network they use, so network internet in general is unreliable and sometimes laggy. And the order in which this save operation occurs might really get messed up. So for example, here the first user is able to save the first value first, as you can see at the top there on the database. But it is immediately being overwritten by the second user's first value. And then since maybe the network for user one here is a little laggy, user two is able to save his second value to the database next, which then subsequently gets overwritten by user one after its network recovers. And with this sort of like a sequence of events, due to network the unreliability of the network. As a result, you can see that the rule in this case in the database is actually broken. And so the data got corrupted and is inconsistent. This is not great, especially like if we're talking about like if this is a bank account transfer operation involving like millions of dollars between two users. So in order to protect the objects so that things like this don't get screwed up, like I think a lot of us know, like we use database transactions to make sure objects are saved together as a single unit. And this will make sure objects that are not saved independently, such that things won't get messed up like what we had before. So here, for example, we still have our two users trying to save the different objects at the same time. However, this time user 1 is able to save all its objects in one go within the transaction. This is followed by user 2 saving its objects within the transaction. And since objects are saved as a unit each time, there's no chance for the rules to be broken inside the database. And so this brings us to the fourth characteristic of this gatekeeper pattern. And that is the set of objects must be saved to the database, like within a transaction. So let's summarize this gatekeeper pattern a little bit. So number one, there is a rule that spans across a set of objects. Right? Number two, there is one object that acts as a gatekeeper that enforces the rule. Number three, the set of objects cannot be referenced by any object that is not within the set. And then number four, the set of objects must be saved to the database with a transaction. So some of you who are familiar with event sourcing should immediately recognize that the pattern that I'm talking about is actually the aggregate pattern. So the aggregate pattern is a set of objects that should be saved together as a unit. And access to any of its objects must go through its gatekeeper, which is called the aggregate root. So this set of object forms a consistency boundary where the object within it is kept highly consistent. And these objects together should be, again, it should be saved as a transaction. So the aggregate pattern is a very important concept and pattern, and it's used if some objects have to be kept absolutely consistent whenever it's updated. It doesn't matter through code, through database, or whatever. Like it has to, like these objects, these entities have to be kept consistent. Otherwise, it's going to be really costly for the business. And the primary goal of an aggregate is to enforce business rules and keep the data consistent. We're going to explore more about this in the next few sections. And so now that we talked about how great aggregates are, let's take a look at some of its drawbacks. So since everybody likes to keep data consistent, and an aggregate can reliably ensure that, so why don't we just draw like a humongous, like a consistency boundary across all the objects within all our, like all the different business departments in all our systems, right? So one huge mega aggregate to rule them all. So this aggregate can contain like millions or even hundreds of millions of objects. And even though there are many rules that has to be enforced from top to bottom in interdependent, like interdependent relationships, you would still have one single aggregate root at the top to rule them all and keep them all consistent and in line. So other than how eerie this sounds, there are many reasons why this is not a good idea at all. So firstly, remember aggregates should be saved and loaded from the database as a unit. And millions of objects are going to be extremely huge in size, and it will take forever to transfer across the network. Like, will all these objects fit in the memory at the same time? Like, this is pretty questionable. And what if you only need to update one single object out of the millions of objects? This is also like a complete waste of bandwidth, and it will take forever to load the whole thing up, change one tiny piece, update the whole thing back again to the database. And a second problem is, like, in order to keep things consistent, remember how aggregates have to be updated within a database transaction. So a database transaction essentially holds a lock to, like, say, like a set of rows, even tables sometimes, like that is updated. And that cannot be acquired by anyone else until the transaction completes their update. And in this case, the transaction essentially locks up the entire like a database along with its millions of records. And it does so in order to protect the integrity of all of them from other transactions in case they update rules that break any rules within the aggregate. And this means that while one user is trying to save update the aggregate, you may have to queue up in line with other users for that transaction to be completed and the log to be released. And since this aggregate contains objects from the entire company, right, I'm willing to bet that there's going to be a lot of people worldwide who's trying to change this aggregate at all times. So say if there's one person per second who is trying to change this aggregate, but on average it takes more than 1 second to change it, then you're going to have like a growing long queue of update requests that's not going to be cleared anytime soon. And users are going to be experiencing timeouts, super slow performance, and making the system unusable. The third problem is that I can't imagine like what kind of mess the code base here is going to be like if everything has to go through the single aggregate, right? If you have thousands of classes representing millions of objects, let's say like each object has one function, like your aggregate root will still have to have like thousands of methods so you can redirect the call to the right objects. The code for this is going to be like super messy. And when you mix in so many different concerns from different user departments, their language, their concepts are going to be different. The code base can get really hard to understand when terminologies mix up and all that kind of stuff. So, and that's not even like I haven't even talked about how like the aggregates have to help enforce the business rules like top to bottom as well too in this case. So the code base is going to be a nightmare to maintain. So it looks like having one single aggregate to rule them all is not really a good idea, right? So what should we do? So even though this huge cluster can clearly enforce every single rule in the application, it is also clearly too massive to be used in real life. Like operations around it is going to be too slow. So let's say we want to split this aggregate up because let's just say that it is giving us a lot of performance headaches and the code complex and there's also like a code complexity problems. In this case, the aggregate root at the top is the only object that can be called by external objects. And it's the object that also ensures that the rules are going to be enforced. And with this kind of structure, we can be very sure that the rules and data are going to be kept consistent. But even though it is able to enforce all the rules, it doesn't change the fact that the aggregate here is still like slow and complex. So we should break this up into smaller and more manageable aggregates. But how do we approach this? Right? In this simple case, we see that the rules within the aggregates can be cleanly separated into 3 different trees. And it looks like the parent of these trees can likely break off and enforce the rules on their own. And furthermore, the root at the top probably doesn't need to hold on to the references to the trees below. So it's foreseeably simple to separate these 3 trees into 3 separate aggregates. The root of each of these aggregates can be the contact points for external objects. And this keeps the objects inside it consistent, like within their own boundaries and rules. And in this case, we're also we're able to split up the big aggregate into smaller ones, but at the same time preserve the rules so that they can still be enforced within their own smaller aggregate. So this potentially also simplifies our code base and improves performance by breaking them down into smaller units. This is great. And so now let's take a step back and take a look at a slightly more complicated scenario. So here we are back to our large cluster aggregate, which again is giving us a lot of a performance and code maintenance headaches. There are still 3 trees that have their own rules, but the whole aggregate is managed by the root at the top. So what if there was actually another rule that spans across all three trees? So this new rule at the bottom states that the color between these trees have to be different. And this rule spans across all three of them. When this new rule is part of like one single large aggregate, it's easy to enforce it because the root at the top is aware of the rule and has the ability to update and validate to make sure the rule is enforced. However, if we have to break this tree down due to performance issues, then we will have a rule that kind of spans three separate aggregates. And even though this breakup will lead to better performance and simplicity, this is somewhat a tricky situation. This is because each aggregate can guarantee consistency within itself, but none of them are able to enforce rules with others because they don't reference each other. And this can lead to a situation where the rule can break. So let's say we have a few external objects that are calling the three aggregate roots separately. So in this case, you can see that each of them are separately called by external objects. The aggregate at the top is called by an object to update its color to red, and then the bottom ones are separately updated to blue, which it's all valid within their own aggregate. But the new rule at the bottom is now broken because none of the objects are able to enforce it on their own and to coordinate it. So there's nothing that aggregates can do because they don't reference each other, and they're not kind of saved as one unit. So it looks like we got ourselves into like a catch-22, like in this situation. For a large aggregate, if we have a rule that spans across many objects, this leads to tight coupling and often like a centralized, a slow, a complex system. However, we can still guarantee that all the rules would be consistent and satisfied. On the other hand, if we break this aggregate down into smaller ones, we can loosen up the dependencies and make it scale better with like a less overly centralized code. However, sometimes the rule might become inconsistent. So looks like there's no real like a win-win like in this scenario. Or maybe is there another way? So when we talk about data consistency, there are generally two different extremes. One is known as transactional or strong consistency, and the other is known as eventual or weak consistency. Transactional consistency is where the data involved would never break the defined rules or constraint. And aggregate is great at maintaining this kind of consistency because it uses transaction and has a single rule that enforces it's a single root object that enforces the rule. However, when things are scaled, this type of consistency tend to break down, making the application slower to run. And the database and the code more complex to change. So while transactional consistency tries to ensure data is never inconsistent, eventual consistency, on the other hand, is the yin to the yang of transactional consistency. So eventual consistency embraces the fact that data can sometimes be inconsistent, but has a process in place to fix it eventually. And in exchange, it can typically scale better and lead to simpler and more decoupled code bases. An example of transactional consistency is when you, say, transfer money between your own bank accounts, right? You often see that the money is deducted from one account and added to another account like immediately, right? Into the correct accounts. So on the other hand, an example of eventual consistency is when you have to wire money abroad to a friend's account who is living in another country. You often notice that your own account balance is going to be deducted at that point of time, but your friend's account has not been added immediately, right? However, eventually, say maybe around 1 or 2 days, your friend's account balance is going to be added by the correct amount. And this is eventual consistency. And it embraces the fact that, okay, data can be inconsistent for a while, but in exchange, you get much better scalability and usually simpler code base and architecture. But problem with that is that since things don't happen immediately, eventual consistency may need to undo previous operations or apply compensating actions in order to fix things that have happened already. For example, so again, if you wire some money to your friend abroad, and maybe it turns out that his account is actually frozen by the time it reaches there, then the banks will have to reverse all the actions and deposit the money back to you. I hope it does, right? But with transactional consistency, if you try to wire the money to an account that's frozen, you would probably have gotten an error right away, right? So yeah, that's generally the problem with eventual consistency, that there are a lot of other complicated actions and processes that you have to do, in case of things just not happening as you expect. So let's take a look at this in action with our previous examples of the small aggregates. So here we have, again, our example before, where we've got 3 aggregates and each one of them has their own rule that it enforces. And remember, an aggregate is always changed as a unit within a transaction, so that either everything is updated or just nothing at all. In this example, since there are no cross aggregate rules, right, the aggregates will be able to enforce the rules and make sure the colors of each object within their aggregates stay the same. Okay. However, things are not so simple here when we added a cross aggregate rule to make sure that the aggregate colors are different. And since the cross aggregate rules are not protected by a transaction, there is no guarantee that the rule can be satisfied at all times. So in this case, right, again, the 2 aggregates at the bottom have the same color and it breaks the rule. And remember the reason, let's go back and remember that the reason why we want to split this large aggregate up into smaller pieces is to improve the performance and simplify the code base. To introduce eventual consistency, what we can do instead is to introduce a service or a process that acts as an orchestrator that can help enforce the rule. And we call this a process manager. There are other names as well too. So maybe a Saga, maybe a reactor as well too. But in this case, we're going to call it a process manager. What the process manager can do is to query or listen to the aggregates for changes and see if the rules, and after it collects all that information, and see if the rule is actually broken or not. So how the process managers actually queries or listen to the aggregate doesn't really matter at this point right now. It could be done by polling the database, or maybe a subscription to some sort of a PubSub, like a message queue or stream. The key point here is that the process manager needs to know what the aggregates are like in order to evaluate the rule. And in this case, it's able to see that some of the aggregates have the same color, right, which breaks the rule. At this point, it's still okay in the world of eventual consistency, as long as the business and other stakeholders are good with rules being broken sometimes temporarily. It's going to be okay. The keyword here is temporarily. What the process manager can now do is to fix the state to enforce the rule. So in this case here, it can do it by issuing a request to update the aggregate on the left side to a different color. Notice how that even though like the aggregate on the left side has been updated to another color, the color within the process manager itself is still its old color. And this is because the process manager will always receive data that will be just a little bit older or stale compared to what the aggregate really is. This is just a natural part of the fact because it's never part of the same transaction as the left aggregate, and so there's always going to be delay. Depending on how this whole thing is designed, the data can be just maybe like a few milliseconds out of date, or it could be like over a week or months out of date. So it really depends on how you design it. But once the process manager queries or listens to the latest changes, then it sees that the aggregate on the left is updated and knows that the rule is now satisfied, and no more further action needs to be done. So eventual consistency is what we demonstrated here. It's a way to keep some rules somewhat enforced when the business doesn't require things to be immediately correct, and data can be stale or out of date temporarily. And this helps make the system a lot more loosely coupled, which can be great for areas that are experiencing a lot of complexity and performance issue due to like just overly centralizing things. So does this mean that we should embrace eventual consistency everywhere in our application? So most definitely no, not at all. And as you saw, writing process managers and dealing with stale data compensating actions can also introduce a different kind of complexity. And it's not always trivial to design and implement it. And there are going to be more use cases that you need to consider and extra code to write and maintain. So you definitely need to find a balance between transactional versus eventual consistency. So previously, when we have to decide between like a large or a small like a aggregate, it was about deciding between like whether to keep the data consistent or inconsistent. With eventual consistency and patterns like process managers, it's more like a decision between transactional consistency and eventual consistency. And whether you choose when you choose like a large aggregate, we're talking about like having more like a transactional consistency within its boundaries. And when you split the aggregates into smaller parts, you're going to be embracing eventual consistency more. So whether you choose like a large aggregate or a set of smaller objects is going to determine how your application is going to scale in different scenarios. So should we put all objects within the same aggregate like what we have here before? Or maybe should we kind of litter small aggregates like here and there and everywhere? Or maybe like we should design our aggregates to be somewhere kind of in between, not too small, not too big. Yeah, again, the decision of how to form these decisions, like these consistency boundaries, is almost an art form on its own because it's determined by so many different factors. And this is also the area where, as developers, we need to have stronger collaboration with our business counterparts to discover kind of like the insights about the business that will be required to resolve this. So in the following section, I'm going to go through like a rather simplistic method of how to draw up these kinds of boundaries. It's not scientific by any means, but it's a process that I would personally use and will give you a taste of what it takes to make these decisions. I've also somewhat simplified it so that it's easier to understand. So step out of trying to find what the consistency boundary is. So the first step is for every rule, right, you try to draw a boundary around the objects that are part of the rule. Okay, the boundary represents a potential aggregate. So say here, we have 3 rules on each of these 3 objects, right? So for each rule, we draw a boundary around the objects that are involved. And we continue to do so for every rule. And if there are boundaries that overlap with other boundaries, we want to replace them. We want to replace them with new ones that forms a union of all the boundaries. So, for example, we have a new rule at the bottom that crosses all 3 boundaries, and we should be forming a boundary between all these 3 objects. So here, okay, we want to form boundary like that encompasses all the existing boundaries like this. And this is the union of all the boundaries that intersected with each other previously. So the second step is that for each object in a boundary, like we need to determine if it needs to be decoupled from all the other objects, right? Loose coupling between objects is usually needed for a few reasons. Firstly, like possibly like a higher scalability is needed, but also like to simplify code bases that are often very complex or getting more and more complex. The high scalability is often only required for certain objects. Usually, when a large number of users need to update a single object at the same time. And this can cause like a lot of contention and excessive locking in the database, and which slows down the operations. Right? So it also slows down the operations of other objects that don't require high scalability, because being in the same boundary means that they are safe together in a transaction. And so decoupling these objects from the rest allows it to reduce contention and scale on its own. On the other hand, that is a part of a big aggregate can be complex when its logic is centralized and is a part of like many interdependent components. And this can make the code a lot harder to understand, and which in turn slows down how fast you can actually change it. Decoupling objects like this that might be complex can let it grow on its own pace while not affecting other objects. So if we have identified a set of objects that needs to be decoupled, so say this one, that needs to be decoupled from the rest, we should redraw the boundary such that it's separated from the rest. So step 3 is we need to determine like if there are any for all the cross aggregate rules that we have, whether or not they can be eventually consistent. So again, cross-boundary rules are like the one at the bottom are essentially cross-aggregate rules. And remember that these rules cannot be naturally satisfied immediately because there are just no transactions across all these objects. So in order to enforce this kind of rule, we have to do it in an eventually consistent manner, which we previously did with a process manager. And this may or may not be acceptable in your business because it will introduce complexity like stale objects and compensating actions. And you will need to discuss this with your business user and also your technical team to see if it's worth making it an eventually consistent process. But if the answer is yes, and the rule can be satisfied in an eventually consistent way, then you'd want to mark this rule as something that will be eventually consistent and move on to the next rule. But however, if the answer is no, then you have to decide whether you'd want to give up the benefits that the decoupled objects can give you. So the scalability, the performance, the more decoupled and simpler code bases that we talked about. Again, your business users and technical team will have to collaborate together and discuss this because it will not be possible for this object to be both decoupled and the rules to be transactionally consistent at the same time. Something just has to be given up. Another alternative to this is that you can and you should like explore also redesigning your object model and your business domain model so that this can be satisfied. And if this doesn't work, then you have to go back to your business users and see if the requirements of the rule can be changed or the object models themselves can be changed. While like some of you may think that like business requirements are always like 100% correct and has to be followed like right to the dot, but you may be first surprised to learn that most business users are quite flexible, and this is a chance to let them know that like not all requirements can be satisfied. You should also be aware of like sometimes what we call fake requirements or ones that business cannot explain why it has to be done. You should try to understand what the business value is and talk to the business user and help them to understand that, okay, if we keep this business use case, if we keep this rule, then it's going to inflict a lot of pain and complexity and cost to ourselves as developers as well too, and our cost and our speed to market as well too. It's also part of the equation when it comes to business value. So we really have to compare what the pros and cons are in it and see which one like the business would decide as a team, right? So not just deciding it on your own, but doing it with your business users. And as a team, you guys like need to decide like what is the best for the business. So the final step is that if all the boundaries are confirmed and the business and the tech teams are both satisfied with it, then these boundaries can be your aggregates. And now you have successfully drawn up all the boundaries of your objects and aggregates. So in summary, the steps of drawing up consistency boundaries of your aggregate can be done in these following steps. Step one, on the top left there, we first draw out the boundaries surrounding objects by the rules that span across object. We want to kind of merge these boundaries, if there are, that span across multiple boundaries. Step two is that we identify any objects that needs to be decoupled from the rest. And again, usually you need it when functions that need, like for functions that need to be scalable or has really complex code base. Step three is for rules that span multiple boundaries and decide whether it can be eventually consistent or not. If not, go talk to your business users and your team to decide whether we need to give up the benefits from loose coupling, or whether or not like we can or like we need to redesign the object model. And then step four is that all business rules are now like can now be either transactionally or eventually consistent. And the boundaries that we drew now, like form your aggregates and make sure you can, and also like make sure you mark all the rules that need to be eventually consistent. Okay, so to summarize the first part of this two-part webinar series, we first discussed the importance of data consistency and explored how application patterns and concepts are not generally well understood in the industry. We then examined like the troubles of enforcing rules across multiple objects and introduced the aggregate pattern, which helps keep the data safe. We then explored the problems of aggregates that are too large and how it can slow down applications because of its reliance on transactional consistency. We then explored how cross-aggregate rules can be prevalent in systems where there are too many small aggregates and how it can lead to inconsistency. We then took a look at how eventual consistency and process manager can help enforce consistencies within rules that are cross-aggregates. And then we checked out the pros and cons between transactional and eventual consistency. And then finally, we looked at a rather simplistic method of how to draw up consistency boundaries, which would decide like which rules have to be handled transactionally or eventually consistent. So in the second part of the webinar, I'm going to build on the concepts that we learned today, and sourcing aligns with these concepts. When we're going to use, when we should and should not use event sourcing, and then we will apply everything that we learned to a unique constraint example where we can go through the different trade-offs and scenarios. So with this, I want to thank everyone for being here and listening today. And I hope you've all learned something new today.
Thank you so much, Stephen. If you've got any questions, please feel free to add them in the chat now. As Stephen said, we will hopefully put together the next webinar at the beginning of next year. Do you think, Stephen? Maybe
hopefully, yeah.
February. Perfect. Okay, no questions, but if you have any, please feel free to ask us. We can get back to you. And if not, everyone have a lovely festive period, and thank you so much for joining us.